So now that we've finished talking about exponential functions, let's dive into logarithmic functions. Logarithmic functions are the inverse function of exponential functions. So let's do a quick review of inverses. Back in chapter 1.9, we studied inverse functions. The function denoted f inverse of x is the inverse function of f of x if for every ordered pair a comma b that exists in f of x, there is the ordered pair b comma a in f inverse. In other words, every single ordered pair flip-flopped. The x values became the y values became the x values. This means that the domain of f inverse is equal to the range of f of x. And similarly, the range of f inverse is equal to the domain of f. In order for a function to have an inverse, it must be one-to-one. This means that each value of the dependent variable corresponds to exactly one value of the independent variable. In other words, the function must pass the horizontal line test. And you might also recall that the composition of inverse functions must always simplify to x. F of f inverse of x equals x, or f inverse of f of x will also equal x. All right, so this is what we studied back in chapter 1.9. And to find inverses algebraically, we followed these steps, right? We wanted to make sure, one, our function passed the horizontal line test to determine that it had an inverse. Two, we interchanged the roles of x and y in the equation. Three, solve the equation for y. Four, replace y with the notation of the inverse, that's f inverse of x. And five, if necessary, restrict the domain so that it matches the range of f of x. Well, so how does this relate to our logarithmic functions? The logarithmic function with a base of a is denoted by f of x is equal to log base a of x. Make sure you understand how that is said, log base a of x, where x is greater than 0, a is greater than 0, and a does not equal 1. Here is our definition right here. Y equals log base a of x if and only if x equals a to the y power. All right, notice, look at that. X equals a to the y power. That is the inverse of y equals a to the x. Notice all we did there is we interchanged the roles of x and y. In the last section of the chapter, we had functions y equals a raised to the x power. Here we are dealing with x equals a to the y. Again, we interchanged the roles of x and y. Y equals log base a of x is the inverse function of y equals a to the x. And these are two different forms that represent the exact same function. Y equals log base a of x is our logarithmic form, hence the log, and x equals a to the y is called our exponential form, hence the exponent. All right, these two forms are equivalent. They mean the exact same thing. That's why in our definition, it says y equals log base a of x if and only if x equals a to the y. Again, two different forms of the exact same thing. Logarithmic form is preferred as we are able to isolate y as a function of x. Again, just like when we were graphing in your calculator, you need to be able to write y as a function of x. So, what do logarithms actually represent? Well, logs, this quantity right here is actually referring to an exponent. Notice y is equal to log base a of x. Well, what is y actually? Y is an exponent. Therefore, this log is representing an exponent. All right, logs mean exponents. So let's see if we can't rewrite a couple expressions to help us simplify logarithms. First, let's start work with going from one form to another. Write the logarithmic equation in exponential form. Log base 7 of 343 is equal to 3. Notice, if we want to go from y equals log base a of x to x equals a to the y, the base of the log becomes the base of the exponent. The quantity, the singular quantity on the other side of the equation, becomes the exponent, and we set that equal to the value that's inside of the log. In other words, we take 7, we raise it to the third power, and set it equal to 343. 7 raised to the third is equal to 343. The same expression, just written in a different format. Logarithmic form, and here exponential form. Log base 16 of 8 is equal to 3/4. Again, let's write the logarithmic equation in exponential form. We take the base of the log, we raise it to the power of the other side of the equation, and set it equal to the quantity inside of the log. 16 raised to the 3/4 is equal to 8. And one more here, we have log base 8 of 4 is equal to 2/3. Again, we take the base of the log, we raise it to the other side of the equation, set it equal to the quantity inside of the log. 8 raised to the 2/3 is equal to 4. Now, we can also go the other direction. Write the exponential equation in logarithmic form. 13 squared is equal to 169. Notice again, the base of the exponent becomes the base of the log. So this is going to be log base 13 of 169 is equal to 2. Remember that the power here is what the log will equal. Log base 13 of 169 is equal to 2. How about another one? 9 raised to the 3/2 is equal to 27. Again, the base of the exponent becomes the base of the log. This is log base 9 of 27 is equal to 3/2. Again, logs represent exponents. This log base 9 of 27, is representing this 3/2 exponent. And one more here, 4 raised to the -3 is equal to 1/64. This is log base 4 of 1/64 is equal to -3. All right, so that's just rewriting the expressions in different forms. Okay, so let's evaluate the following logarithms now. Log base a of x means a raised to what exponent equals x. So for example, here if I'm trying to evaluate log base 7 of 49, this is saying 7 raised to what exponent is equal to 49? Well, as you guys all know, 7 squared is 49. That means that log base 7 of 49 is equal to 2. Again, remember that logs represent exponents. What exponent? 7 raised to the 2 power, 2 is our exponent, is equal to 49. Log base 3 of 27. This means 3 raised to what exponent is equal to 27? Well, if we go by multiples of 3, 3 times 3 is 9, times 3 again is 27. This means that log base 3 of 27 is equal to 3. How about log base 2 of 32? Again, this means 2 raised to what exponent is equal to 32? Well, let's go by our multiples of 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Log base 2 of 32 is equal to 5. Again, 2 raised to the 5th power is equal to 32. Log base 4 of 2. Now this one's a little bit trickier. 4 raised to what exponent is equal to 2? 4 raised to what exponent equals 2? In this case, our answer is 1/2. Recall that fractional exponents give us roots. A 1/2 exponent is actually the same thing as taking a square root. The square root of 4, 4 raised to the 1/2 power, is equal to 2. So sometimes these can get a little bit tricky. All right, here we have log base 32 of 4. What does this equal? 32 raised to what exponent is equal to 4? For more difficult logarithms, it can be helpful to create a logarithmic equation and then rewrite the expression in exponential form. All right, so let's write this as a logarithmic equation. Let's just say log base 32 of 4 is equal to y. All right, this is some value of y. And you could pick any variable that you want. I have simply picked y because we have our function written in exponential form is a to the x is equal to y. So let's now write this in exponential form. This would be 32 raised to the y is equal to 4. Now what we can try to do is to rewrite each side of the equation as an exponential quantity with the same base. We actually did this before in the last section of the chapter. That will allow us to use the one-to-one property for exponents, where if the bases of my exponents are equal, then the powers must be equal. Well, what common base can I rewrite each of these with? Each one can be written as a base of 2. All right, 2 to the 5th power is the same thing as 32, and 2 squared is the same thing as 4. So I have 2 to the 5th raised to the y is equal to 2 squared. Remember that powers raised to powers, you are going to multiply them. This would be 2 to the 5y is equal to 2 to the 2nd power. Using the one-to-one property, this means that 5y is equal to 2, and that y is equal to 2/5. All right, that means log base 32 of 4 is equal to 2/5. 32 raised to the 2/5 power is equal to 4. Let's try another one here. Log base 3 of 1 over 81. This means 3 raised to what exponent is equal to 1 over 81? Again, for more difficult logarithms, it can be helpful to create a logarithmic equation and then rewrite the expression in exponential form. Well, how are we going to do this? Let's set log base 3 of 1 over 81 equal to y. Now, write it in exponential form. 3 raised to the y power is equal to 1 over 81. Now we can try to rewrite each side of the equation with the exact same base. Well, as we said before, fractions can be a little bit difficult to work with. So let's start off by writing this as a negative exponent. We would have 3 raised to the y is equal to 81 to the negative 1. Again, remember, negative exponents give us reciprocals. Now, can we rewrite 81 with a base of 3? Right, we've got this base of 3 on the left-hand side. Maybe we can write 81 with a base of 3. Well, 81 is 9 times 9, which means that that's 3 times 3 times 3 times 3. 3 to the y is equal to 3 to the 4th raised to the negative 1. And again, exponents raised to exponents, we can multiply them, and that will allow us to use the one-to-one property. 3 to the y is equal to 3 to the negative 4, which means that y must be equal to negative 4. And there we have our solution. Log base 3 of 1 over 81 is equal to negative 4. All right, so there you have a good introduction into logarithms. Again, remember, logarithms are the inverse of exponential functions. In the next video, we're going to talk about some properties of logarithms and get more into solving some different logarithmic equations.